Coefficient of viscosity, like surface tension, decreases on adding soluble impurities. Both coefficient of viscosity and surface tension are similar in respect of temperature and adding impurities. They decrease with rise of temperature and adding impurities. And coefficient of viscosity is 0 for an ideal fluid. Since F is 0, no viscous force, therefore eta is also become 0. Now coming to volume of liquid flowing per second, which can be called as a Poiseuille's formula for a low dense liquid. So volume of liquid flowing out per second is directly proportional to the fourth power of radius of the capillary tube through which the liquid is flowing. Just consider a container containing a capillary tube fixed horizontally. Its length may be L, radius is R, and there is a container for the outflowing liquid. So if it is, the pressure difference is obtained to be at H. The pressure difference between the inner end and outer end of the tube. Fourth power of radius of the capillary tube, volume of liquid flowing out per second here, directly proportional to the pressure difference between the two ends of the capillary tube, inversely proportional to the length, and inversely proportional to the coefficient of viscosity of the liquid. Thereby, I can write volume of liquid flowing out per second is B by R power 4 by 8 eta L. The relation may be smart one, but the questions are coming on varying of any of these comparatively, either changing radius or pressure changing or length changing or nature of liquid having different coefficient of viscosity. They are asking about what is the volume of liquid flowing out per second. These two relations, earlier we have taken the Newton's formula. Viscous force depends on two quantities, area of the surface of the each layer and velocity gradient. Got a relation eta AV dV by dx. Here we got volume of liquid flowing out per second under streamline horizontal flow. Fourth power of radius, pressure difference between the ends of the pipe, inversely with the length, inversely with coefficient of viscosity. Now coming to the third is for dense liquid. Like castron. So the liquid does not flow easily. In such cases, we take a long cylinder in which this oil is taken, dense liquid is taken, and solid ball of definite radius is made to fall through this. Suppose we have some scales correctly mentioned on the container. We see that as the ball falls down, it is experiencing the three forces. One force is due to its weight mg. Another force is force of buoyancy, buoyant force. And another force is due to viscous force, force of viscosity. When mg become equal to force of viscosity plus force of buoyancy, this reaches a maximum speed. It comes under weightlessness. No further changes in the velocity of the body take place. Then it starts falling with a constant velocity. That velocity with which it starts falling downward with constant speed, we call it as a terminal velocity. This called as a terminal velocity. If you draw a graph of velocity versus time, we see that as the ball coming down and down, velocity goes on increases and ultimately it remains almost a constant value. This constant value that the ball attains when falling in a fluid is called as a terminal velocity. So by comparing these equations, substituting the values of liquid density and volume of the ball and its density and viscous force and force of buoyancy, we arrive at the terminal velocity relation as Vt is equal to 2r square g by 9 eta into density of the solid minus density of the liquid, where r is the radius of the ball, rho s is density of solid, rho l is density of liquid, eta is coefficient of viscosity, which suggests terminal velocity for a given liquid is directly proportional to r square and inversely proportional to coefficient of viscosity and directly proportional to difference in density of the solid to liquid. On the basis the questions are appearing in entrance. Along with, for dense liquids, we have Stokes formula, which gives you the viscous force that experienced by a solid moving in a liquid, 6 pi eta r Vt, where eta is a coefficient of viscosity of the liquid, r is the radius of the ball, Vt is a terminal velocity. These are the two quantities. As like in low latency liquid, we have seen the two. Number one, Newton's formula gives viscous force. Poisson's formula given you the volume of liquid flowing out per second. This is giving terminal velocity expression and importance of terminal velocity to understand the viscous force. And what factors terminal velocity depends. These are taking major roles in asking questions in entrance papers. With this we finally coming to Reynolds number. This gives us nature of flow of liquid and its expression is determined V rho d upon eta, where V refers to terminal velocity, rho refers to density, d refers to terminal velocity, terminal velocity, d refers to diameter of pipe, eta coefficient of viscosity of fluid. If this number less than 2000, when we calculated substituting the values for a given liquid, then we say it is a streamline. If this number between 2000 to 3000 in between, we cannot say that whether it is streamline or turbulent, it is switching over or transformation level. If this number become greater than 3000, then it is called turbulent. How we decide the nature of flow is streamline or turbulent is obtained from this Reynolds number. Reynolds number depends on these quantities on which this equation given, and this is the summary of the last unit, the fourth unit of this fluid mechanics is the viscosity. Viscosity is a property of a liquid where it opposes the relative motion of the different layers of its liquid. This viscous force we understand with velocity gradient and considering different layers of the liquid and their area. We come to know in viscous force, Newton's formula for low density liquid, Newton's formula given you the force, viscous force, eta A dV by dx. Similarly, Poisson's formula given you the volume of liquid flowing out per second, on what factors dependent also given in there. For dense liquids where the liquid cannot easily flow through a pipe or a solid liquid, or now we make within the liquid we allow the solid to move, relative motion. So in that case, we define the term terminal velocity. So this terminal velocity, we had a relation, and on what factors dependence we come across. And that help you to know the viscous force given by Stokes formula. And velocity, terminal velocity relation depends on radius square, most oftenly appeared question. And lastly, about the Reynolds number, which decides the nature of flow of liquid. Some questions in first unit, that is fluid statics. Two thin circular discs of radii 3 cm and 4 cm are placed in a liquid at the same depth. The thrust on them are in the ratio. When we read the question, we must be careful. At many times I am telling you that what the data given you perfectly understand, and some terms they specify. Here they given radii. R1 is 3 cm, R2 is 4 cm, are placed in liquid at the same depth. The word very important is same depth. That means if you consider a liquid taken in a container, the two surfaces are same depth. H1, H2 are equal. They are asking about the thrust. Now come to the question thrust, the force. Force you can imagine on the basis of area into pressure. Go to the synopsis. Always start from that, you are understanding better. Both application of mind improves and also understanding of the problem easier. Why we taken? Because they are asking the thrust. Why I taken pressure? Because they are at the same depth. The pressure idea helping us. So therefore I taken pressure equal to force by area, force equal to A into P. And area, circular discs, area can be written as pi r square, pressure can be written as rho gh. If you see this equation, one thing is more clear. Pi is constant, rho is same, g is same, h is same. Only variable for our question is f proportional to r square. R is given, asking f, the ratio can be determined. F1 by F2 is equal to R1 by R2 whole square. That is 3 by 4 whole square. Gives you 9 by 16 is the ratio of the thrust. Option number 1 is the solution. Is a level 2 question. They equated the two different relations. One, you have to know pressure equal to force by area, and another pressure relation Gauss pressure rho gh and area relation pi r square. And given data, h is most importantly how to keep our eye. The word they used, that made you to come to f proportional to r square and your answer becomes simple. Similarly, similar type question. Let's come to the third one. Question number 3. The plane surface having the area in the ratio 1:2 are immersed vertically in a liquid so that their center of gravity are at the depth in the ratio 3:2. Then the ratio of thrust on them. See the case in this, area is mentioned, A1 by A2 ratio given 1:2. Vertically in a liquid so that their center of gravity are at the depth in the ratio. That means they are given H1 and H2 as a 3:2. Again the ratio of thrust on them. Rho same because liquid same. Same depth, same relation. Force is equal to A into P, A into rho G H. I am not changing A because they given the area ratio. Here H is different, H1 and H2. Rho and G common, therefore I can write F proportional to AH. Question is on ratio of the thrust. Ratio of thrust, that is equal to A1 by A2 into H1 by H2. Given A1 by A2 is 1 by 2 and 3 by 2. Answer become 3 by 4. Option number 1 is an answer. It is also level 2 question, appeared question. So let us come to the question number 4. A body floats in water, 0.3 of its volume outside, relative density of body. Question is short, but it is a level 3. So they are saying in a liquid, a body is made to float. 0.3 times of its volume is outside, and the remaining 0.7 volume is inside. They conceptually understood the question. Relative density of the body. I told relative density of a body. So if you go to the question, weight in air by apparent loss of weight in the liquid is difficult. Why I made it level 3? Your original formula is not helping. But body, what is you are seeing is a floating. Use the law of flotation, because relative density of a body means what? Density of body by density of water. Comparing density of body with water. That ratio is important. How we get is not important. So I directly go to the law of flotation. Weight of body in air. Law 6, weight of liquid displaced. So it seems to be unrelated to the question, but it is helping us to find the relative density. Weight of body in air, volume of body entire, density of body, gives you the mass into G, is a weight of the body. Weight of liquid displaced, 0.7 volume, because immersed portion only, into density of liquid into G. V common cancels. Our aim is to get this. What you will get is around 0.7. Others are cancelled. Answer is again option number 1. An ideal good question. Level 3. Why we put in the level 3 also I told, because real equation you are not using. By virtual relation you are arriving at to the answer. So the question number 9, if you see, under same level 3, a cubical block of wood of length 0.2 meter, weighing 6.4 kg, float in water, the depth of immersion is. So they are given a cubical block its mass is given 6.4 kg, its sides are 0.2 meter, it is a depth of immersion is h inside the liquid, 0.2 meter length each side, depth of immersion, the question is on h. This depth is required. Again we use the concept of law of flotation. Weight of body in air equal to weight of liquid displaced. Weight of body they given, however, mass into G. Our one job is easy, one side. Second, volume of liquid displaced, that is water. They told, what is the volume of this portion? You know the base area as a 0.2 into 0.2 equal to 0.04 meter square. Base area into height gives you the volume. That is, I can write 0.04 into h volume. Density of water into G. This is the weight of the water displaced. This is weight of the body in air. Now the solution is G cancels. You want H. This M is 6.4 divided by 0.04 into 10 power 3. This makes 0.64 by 4 equal to 0.16 meter. So your option is first one. So this is the portion which is inside the liquid. Weight of the body as the mass given we written directly as mg. Weight of the liquid displaced, volume of the portion of the body inside the water into density of water. Volume inside calculated knowing the base area into height. Aim is to find height, that help you. Multiplying by G. Substitution and simplification we arrive at 0.16 meter.